Okay, so let me go back now to talk about extremal numbers again, which, if you remember, the extremal number, like this, is meant to be the largest number of edges on any graph with n vertices that does not contain this as a subgraph. Two classes ago, we showed that the extremal number for k sub r was this, where this is the number of edges in this graph. This is the complete multipartite graph. It has n vertices, it has r minus 1 parts, and each part is either the floor of n over r minus 1 or the ceiling, whatever makes it add up to n. Some of them will be floor and some of them will be ceiling, and however it needs to work out is fine. This graph does not contain any k sub r by the pigeonhole principle. If you had r vertices, two of them would have to be in the same part, and then those two would not be adjacent, so it can't contain the subgraph k sub r. And last time we showed that this was maximum possible. In other words, and there's no graph with more edges than this that doesn't contain k sub r. Just a quick word about what this number of edges is. We write it this way because finding an exact formula is kind of annoying because of this floor and ceiling business. But we can approximate it, at least if n is much larger than r, because if n is really a lot larger than r, then rounding up or rounding down doesn't make that big of a difference. These two things, whether it's floor or ceiling, those only differ by 1. And if n is a huge number, then that hardly matters. So the number of edges, if n is much larger than r, is, well, I have r minus 1 parts, so let's just choose 2 of my parts, and I'll tell you how many edges are in between the 2 parts. Well, each part is basically n over r minus 1, and whether you round up or round down, these numbers are so big it's hardly making a difference, so it's basically just n over r minus 1. Whether it's the ceiling or the floor, it's close enough to n over r minus 1. So the number of edges between 2 parts would be n over r minus 1 times n over r minus 1. So that's this. Right, so this, choose 2, that's r minus 1 times r minus 2 over 2, and then I can cancel an r minus 1, and I'll get this. And if I rewrite r minus 2 over r minus 1 this way, I get this. When I say approximate, I can say this more precisely. What I mean is that as n goes to infinity, if you fix r and let n go to infinity, the ratio of this to this goes to 1. That's what I mean by approximately. And this last expression, we like this because, again, for large values of n, this is basically n choose 2. Right? N choose 2 is n times n minus 1 over 2, but for large values of n, that's basically n squared over 2. So this is the total number of edges that any graph could have, and so this number in parentheses is telling you what fraction of the total possible edges do we have, and it's this fraction. And as we continue to talk about extremal numbers, that's kind of going to be a focus of ours, is like, what fraction of the edges do we have? Okay. So, but what I really wanted to talk about was, since Turan's theorem is just for k sub r, it's for looking for a complete subgraph, what if you look at other subgraphs? there's a quick observation that uses the ideal we already used, which is the extremal number of n and h, which again is the maximum number of edges in a graph that has n vertices that does not contain h as a subgraph. That extremal number would be at least this. Why? Because this is the number of edges. If I took h, took its chromatic number, and like let that be r, it's like setting r equal the chromatic number of h, and then drawing this graph. This graph, let me say what I'm trying to say here. The chromatic number of this graph is r minus 1 because, well, I can just give this all the same color, give this all the same color, give this all the same color, and I would use r minus 1 colors. So this graph can't possibly contain a graph whose chromatic number is r, because if you look at a subgraph, the chromatic number of a subgraph is less than or equal to the chromatic number of the whole graph. So any subgraph of this must have chromatic number at most r minus 1. So in other words, this can't possibly contain h, which has a chromatic number of r. So this is a graph that doesn't contain h. So the extremal number is at least that number of edges, which is what we have here. And by the discussion that we just said, for if n is very large and h is a fixed graph, this is approximately this expression. Sorry for the mess I made here. This is just replacing r with chi of h. So we have that lower bound on the extremal number of any graph. And it turns out that that lower bound is essentially optimal in the following sense. We have the Erdős-Stone-Simonovitz theorem, which says that for any h, that the extremal number is less than or equal to. And then we have almost the same thing here, except there's a plus epsilon. I'm not being too formal about my statement of this theorem. A more formal statement is, for all positive epsilon and all sufficiently large n, where sufficiently large can depend on epsilon, this inequality holds. But in any case, in some sense, this is a statement that the lower bound we just observed is optimal. The proof of this is hard. I'm telling myself that we will at least sketch a proof of Erdős-Stone-Simonovitz by the time the class is over. That may or may not happen, but the proof is hard. So yeah, the upper bound is hard, because this one's the upper bound. The lower bound we already observed. But for today, let me focus on a question that this discussion leaves unanswered, which is what happens if the chromatic number of the graph we're talking about is 2. Because if the chromatic number is 2, then if you look at what we said, you know, chi of h is 2, so this is like 1 over 1, and then this number in parentheses is just 0. So basically what we know, if we summarize what we know, even assuming Erdős-Stone-Simonovitz, which we haven't really proved yet, but if we just summarize this, when the chromatic number is 2, the lower bound is telling me that the extremal number is at least 0, and the upper bound is telling me that it's at least, again, if I plug in 2 for chi of h, this is going to cancel this, and I'm just going to get epsilon. So the upper bound is telling me that it's just less than or equal to epsilon n squared over 2, which is not very satisfactory. So what do we look for, and what are our standards when we talk about whether these are good bounds or bad bounds? The situation up here was seeming, I would say, more satisfactory, at least if the if this number isn't 0. Because when chi of h is 2, then this number is 0. But when chi of h is larger than 2, this number is not 0. And we have a pretty satisfactory answer because the lower bound is this number times n squared over 2. And the upper bound is just a slightly larger number times n squared over 2. In other words, I have this... The thing that I'm trying to estimate is sandwiched in between something that's on the order of n squared and another thing that's also on the order of n squared. And if you look at the coefficients, even the coefficients are quite close to each other. Down here, I have something that's less, it's the upper bound seems to be of order n squared, but it's like a small coefficient times n squared. And the lower bound is basically not telling me anything, hardly. I mean, this lower bound is no better than the absolutely trivial lower bound. So in that sense, this is much less satisfactory. So let's do something to attack it. So here's a theorem, the Kovári-Sós-Turán theorem. This is about the extremal number of a complete bipartite graph. Of course, that's an example of a graph that has chromatic number 2, and we're talking about graphs with chromatic number 2, so maybe it makes sense to start with this one. So for all r less than or equal to s, there exists a constant c such that this extremal number is less than or equal to this, which is better than the previous upper bound, of course. The previous upper bound was something, it was like a small coefficient times n squared. And as we're doing this, we're always thinking of n going to infinity. So a small coefficient times n squared, as n goes to infinity, that's a lot bigger than this, because this is a power of n, and the power is smaller than 2. You have to think that n's going to infinity and r is fixed. So this would be a much better upper bound. Okay, so let's prove it. Suppose G has no subgraph KRS, and it has n vertices, and it has more than this many edges. And this is setting up a proof by contradiction. Of course, we haven't really said what C is yet, but as long as we can show that there exists a C where we get a contradiction, then that'll be good enough. So here's our setup for proof by contradiction. And the trick here is to count the following. I'm going to count pairs consisting of a vertex and a set of vertices, R. So V is just a vertex in the graph. R is a set of vertices that are all neighbors of V. And there are little r of them, and little r is the same number as from up here. So that's what we're counting. Maybe I'll draw a little picture. It's like here's V, here's R, and V is adjacent to all of them. And I'm counting pairs, V and R. So on the one hand, and this is going to be like a double counting argument, I'm counting pairs, and there's two ways I can do them. I can sum over V, and I'll add up how many R's go with that V. Or I can sum over R's and ask how many V's go with that R. So here's one way to do it. I'll sum over all possible sets R, and I'll count how many v's go with that r. The requirement for v is that it's supposed to be adjacent to everything in r. So what I would add up is, for each set r, I'll add up the number of vertices that fit the bill for that. In other words, the number of vertices that are adjacent to all of them. Of course, if we're talking about a graph G that doesn't contain a k sub rs, you can't really have that many v's for a single r. If I fix this r, I couldn't have s many vertices v that are adjacent to all of them, because that would be a k sub rs. So when I add this up, for each r, the number of v's that go with it is less than s. Because if there were s of them, then I would have a k sub rs. So this sum is less than or equal to, okay, how many terms are there? There's n choose r terms, because I just have to choose a set of r vertices. And each term is at most s minus 1. Okay. And then I'll just use a simple estimate. Last time we talked about the fact that n choose r is less than or equal to n to the r over r factorial. So I just did that. Okay, that's one bound that we have on this thing, this number of pairs. And as I said, we're going to count it two ways. Now let's count it by summing over v, and I will add up how many r's go with each v. So here we go. I'll add up over v's, and then the number of r's that go with v, because if I already know v, and v has some neighborhood, right, r just has to be a subset of that, right? The only requirement is that v is adjacent to everything in r. In other words, r is a subset of the neighborhood. How many subsets are there of the neighborhood? Well, it's just the number of ways to choose little r things out of this many things. So in other words, this is the degree of v, and I want to choose r. Okay. Now, remember where we were. I want you to remember that we were here, because we were about to take a little detour. Maybe I'll put a star here or something. We were counting these pairs, and we decided that one way of counting it was this. I am about to estimate this. I'm about to say that it's greater than or equal to this, and I have to justify this somehow. Okay, so remember where we were. What I'm about to use is Jensen's inequality. Jensen's inequality, I've written one statement of it here. There are various other statements. This one is simple enough, or it's not too simple for us to use. For f, a convex function, we have this inequality. If you're doing f of, the way I think of this is you're doing f of an average. F of the average value of a bunch of x's is less than or equal to the average of a bunch of f values of the x's. Or yeah, maybe it's confusing to listen to. You can also just look at the formula and interpret it for yourself. Convex is, roughly speaking, to a Calc 1 student, convex means the same thing as concave up. It means that if you draw the secant line between any 2 points, that it lies above the curve. At least if it's twice differentiable, basically that means it's concave up. And so let me call your attention to a specific function that happens to be convex. It's this function. It's this function that I call x choose r, where x is a real number and r is a natural number. Usually when we write this, you know, in combinatorics, we write x choose r when we're counting something, so they're both, how did I write this again? R is a natural number. Usually they're both natural numbers. Right now I'm only requiring the bottom to be a natural number, and I can see that I'm making all sorts of mistakes here. Okay. Maybe I should just start over. X doesn't have to be a natural number here. That's what I'm saying. And I'm going to give a formula that agrees with the formula that we know. Of course, what I wrote up here agrees with what we know. If I was doing x choose r and these were both natural numbers, one way of doing it is to start with x and then x minus 1 all the way down to this over r factorial. That formula also, I mean, you can apply that when x is not an integer. You just plug it in, and you won't get an integer for an answer, but you just plug it in. So we're going to go with that if x is greater than or equal to r, and we're just going to say that it's 0 if x is less than or equal to r. This is a convex function. I won't give, like, really a formal proof, but I mean, the graph of this function looks something like this. Of course, it's just flat up to x equals r, and then this is this is just a polynomial in x. For values of x greater than or equal to r, we're above all the zeros of this, so it's I guess it's it's not even continuous actually, because if I plug in, maybe this should be x is strictly less than r, because if I plug in r here, I'm going to get 1, as I should, because r choose r is 1. But that's fine. It doesn't have to be continuous. So the graph looks something like this. It's flat up to r, and then it jumps up, and this is for x greater than or equal to r. This is larger than all of the zeros of the polynomial. The annoying part is this polynomial has a bunch of zeros at x equals 0, x equals 1, x equals 2. So if I define this as like a non-piecewise function, the part of the graph around here would be annoying. It would cross the x-axis a bunch of times. So I'm sort of cutting that part off and just going like this. And yeah, like I said, roughly speaking, you can verify that this is a convex function just because if you draw any secant line that lies above the curve, like any of these secant lines is going to lie above the curve. Yeah, right. In any case, sorry, I think I'm worrying about this a little bit too much. For us, we're not even really interested in when x is anywhere near r. The values of x we're going to apply this to are much larger than r. The relevant part to check, you can check that the second derivative of this is positive. You can imagine just using the product rule twice to do this, and the first derivative would have a bunch of terms that look like this, except for exactly one of these things would be missing. And then the second derivative would have a bunch of terms where exactly two of these things were missing. But all of the terms would be positive, and the second derivative would be positive. So, okay, maybe I talked about this too much for something that I'm not actually really proving for you, but this function is convex. So, remember where we were. We were here. I am adding up a bunch of function values of like something choose R. And that's a, so it's like I'm doing this. I'm adding up f of a bunch of things, where f is this function. That should be greater than or equal to, if I get this n over, that's greater than or equal to n times this. So n times this. N times this would be plugging the average of these numbers into f. In other words, the average of these numbers, the degree of v. So here's the average of those numbers, and I'm plugging it into f. Right? And that's the application of Jensen's inequality. So now that we're through with that, just remember, of course, the degree sum is just 2 times the number of edges. So this degree sum, we said that there were this many edges, so this is 2 times this, and this has an n to the 2, and I'm dividing by this to n, by n, so this becomes n to the 1 minus 1 over r. Okay. Where are we? We've got this. I just want to estimate this a little bit. This is n times, okay, how do I do something choose r? And maybe let me remind you, indeed, we're talking about x choose r, where x is much larger than r, like we're imagining n going to infinity, so this thing up here is much larger than r. And the way you evaluate such a thing is, you know, it's basically, it's this formula. It's this number times the number minus 1 times the number minus 2. So I take this number times this number minus 1 all the way down to this, divided by r factorial, and it's times n. I would like to estimate that. One thing, yeah, when we do a proof like this, due to the nature of the statement we're trying to prove, it suffices to only prove it for sufficiently large n. If you look at the statement we're trying to prove, if there exists a constant c such that this statement is true for all n that are at least, say, 1 billion, then I can pick a possibly different constant c that works for all n, including the n's smaller than 1 billion. And I would do that just because there's only finitely many values of n, you know, to make, basically, to make this statement true for all n, I just need to choose a larger value of c to guarantee that it's true for all n from 1 to 1 billion, and then from 1 billion on, I'm all set because we already had a constant that worked for n greater than or equal to 1 billion. So, in other words, when you're proving a statement like this, it suffices to only prove it for sufficiently large n. And for sufficiently large n, this inequality is true. And this follows from just sort of, I would say, yeah, almost like basic calculus, but I'm going to be hand-wavy about it. For n sufficiently large, again, n to this power is going to infinity, so this number minus 1, the 1 is hardly putting a dent in this number. This number minus 1 is very close to this number. So basically, what I did here is I kept the r factorial in the bottom. I replaced... Do I have... Okay, I'll just keep using blue. I said this one is less than or equal to c times n to the 1 minus 1 over r, because I just dropped the 2. I said this one is also less than or equal to c times n to the 1 minus 1 over r, because basically the effect that this 1 has is a lot smaller than the effect from dropping this 2, because when I dropped this 2, that makes this smaller by a lot. It makes this smaller by c times n to the 1 minus 1 over r, which is something that's much larger than 1. That has a much larger effect than subtracting this 1. In fact, everything in here, the thing that I'm subtracting has a much smaller effect than dropping the 2. So I just said each one of these things is less than or equal to c, whoops, yeah, sorry, I'm really messing this up here, greater than or equal to, greater than or equal to c times n to the 1 minus r. And right, if I multiplied this all together, you can see that I get c to the r. I would have an n to the r minus 1, and then with this n, that makes n to the r. So that's how I got that. And then this is true for n sufficiently large. And so where did we get ourselves? We were counting these pairs. We were counting pairs v and r. And on the one hand, we decided that the number of pairs was less than or equal to this. And on the other hand, we decided that the number of pairs was greater than or equal to this. So this is less than or equal to this. So that's what I wrote here. And this is going to give me a contradiction for an appropriate choice of c. Remember, we just have to show the existence of a c such that this gives me a contradiction. Both sides have n to the r. Both sides have r factorial. So if I choose c to the r to be bigger than s minus 1, which is going to be possible, the only requirement is that for all r and s, there exists a c. C is allowed to depend on r and s. So, just make c bigger than the rth root of s minus 1, I guess. And that's a constant that works, and to give us a contradiction, and so we're good. Okay, so then maybe I'll leave it at that for today, because these... I think I'm trying to do too much.